Hello students, this is the third and final part of the final exam review for elementary statistics, MAT120. Hopefully you tried the sample final already and you're just coming here to check your answers. If you haven't already done so, please try to complete the final and then check your answers. These are the answers for questions 21 on. We already did up to 20, so here's number 21, 22, 23, and 24. There wasn't a whole lot of differences between the first couple and these. It's asking here, if vending machine will only accept coins weighing between these two values, which percentage will be rejected? We're looking for between 5.48 and 5.82. That's the percentage that they give us here. But that is all of the coins that are accepted. They accept coins weighing between these two values. Then they're asking what percentage of legal quarters will be rejected. So it's the complement of that 1 minus 0.9806. It's looking for 0.5% and 0.5% lowest and highest. It's trying to figure out the cutoff weights. So they're giving us percentages or area under the curve, so we need to use INV-norm. The first argument is the area under the curve, the second argument is the mean, and the third argument is the standard deviation. We're getting 5.4897, so that's the lower bound. It's looking for the highest 0.5%, in other words, 0.5% away from the maximum, which is 100%. 0.995 represents that value, and then the same mean, same standard deviation, 5.85 is the answer there. Again, a normally distributed problem, and it's looking for a percentile rank, and it's looking for a cutoff score. This picture is designed to help you figure out what's going on. 15% of the top recruits are going to get accepted there, so we put into our calculator 0.85, 62, and 8. We're using 0.85 because the INV-norm calculation always figures out the area behind a certain value. So this 0.85 represents the area behind this value. And our mean and standard deviation are here. And it's obviously the 85th percentile because 85% of people scored below it. Percentile talks about, what percentage of people are below it or what percent of values are below a certain number. Moving on to question 23, it talks about an average of $62 per week on groceries, which is actually pretty good. It asks for the middle 50% of one-person households. So I know that 62 is going to be the mean. That's going to be the middle of this normally distributed distribution. In order to find out these other two values, this lower bound and this upper bound for that 50%, we know that 50% is going to be here. That means 25% is going to be in this tail. 25% is going to be in this tail. So the first INV-norm I'm going to do is for the lower 25%. I'm going to use 62 and 10 because those were the values that were given to us for mean and standard deviation. So 55.26 is that lower bound. Here, I'm not going to use 50% and I'm not going to use 25% again. I'm going to use 75% because that 50 and this 25 together are below this value. So I'm going to use 75% or 0.75 in my INV-norm. For number 24, it's another normal distribution question. It gives us average income, it gives us the standard deviation, and then it asks what percentage of families earn below 25,000. Percentage of families, probability, proportion, they're all asking for the same thing, the area under the curve. So normal CDF, the lower bound, the upper bound. In this case, we're looking for the upper bound of 25,000. This is the mean, and this is the standard deviation, and we get 0.1232, and we convert it into percentage because that's what it asks for. Question 25. It asks us about the volume of soft drinks in plastic bottles. The first question asks us to do a regular normal CDF. I won't explain that because we just did. A random sample of 25 bottles. This is going to be a little different because we're not talking about one bottle, we're talking about 25 bottles. So the mean and standard deviation of this sampling distribution is going to be a little bit different. The mean is the same center, but the standard deviation is going to be lower. Now I want you to think about this. If you collect more and more things in your sample, that means that the average value that you come up with is going to be closer to the mean than if you just pick one bottle. One bottle has the potential to be really weird, very, very small, for example, or very, very large. But if you take 25 bottles and average them all together, the chances of them being weird, the chances of them being extremely low or extremely high is lower. So that means our sampling distribution is going to get higher in the middle and closer. The standard deviation is going to go down. So that is the for letter B. Now for letter C, it asks us to do normal CDF. The only thing that changes from A to C is it's asking for less than 15.8 ounces, so we're using a different lower bound. And we're also changing our standard deviation because 25 sampled bottles, that changes our standard deviation to 0.12. That's the calculation that's shown here. For question 26, it tells us the average is 17.6 pounds, assuming normal distribution. These are very similar types of problems. For letter A, you use normal CDF. For letter B, it's asking for the same thing. A family selected at random. My sample is size 1, so I don't have to change the standard deviation. It's 3.5 divided by the square root of 1, which is just 3.5. The sample of 35 families, now this is a horse of a different color. So the sample size is 35, so we're dividing the standard deviation that we were given by the square root of 35. That's how we get our probability. Confidence intervals are estimated in the same way every time. We're using our statistic plus or minus some sort of critical value, whether it's t if we're dealing with means, or z if we're dealing with proportions. S is the standard deviation, n is the sample size. Now that we have all that information, we just basically plug it all in. The margin of error for the 90% confidence interval, we know that 90% confidence interval means in the tails it's 5% each. So there's 5% to the left, 5% to the right, because it has to equal to 100% in the end. The degrees of freedom is n-1. In this case, n is 10 randomly selected newborns, so 9 is the degrees of freedom, and we plug it all into the calculator. This piece I'll show you how to do in the calculator right now. So I have my calculator out here. I'm going to go into stat. I'm going to go to tests. I'm looking for the t interval, which is a little bit down here, t interval. I am going to plug in all of my stats, my x bar, my sx, my n, and my confidence level. You can see here that I put in all the information. 7.14 is my x bar, my sample standard deviation is 0.87, the n is equal to 10, my confidence level is 90%, 0.9. So I'm going to go down to where it says calculate. And now on the notes here, it says 1.8331 is the critical value. You can find that using the calculator on a different screen, but not necessary to find the confidence interval. Here's the confidence interval, 6.6357 and 7.6443. I rounded a little bit here. But that's our confidence interval. Not too bad. The next part asks us whether the confidence intervals provide sufficient evidence that the mean weight of a newborn is above 6.5 pounds. Everything in our confidence interval is above 6.5. So we say yes. The lower bound is 6.636 and 6.5 is less than that. If we increase confidence level, anytime you increase confidence level, the net or interval increases. If I want to be more confident, I make a bigger interval. I'm 50% confident that you all have a grade that's between A and C. I'm 100% confident that you all have a grade between A and F. An editor wants to estimate the average number of pages, and we want within 20 pages. That's our margin of error. Margin of error calculation is here, so all we have to do is plug in numbers into the margin of error calculation and find our n. It's detailed here. It's simply just a math problem, and since you guys are very good math students, I'm not going to go too hard into why it is that way. It asks for a variable and individual. The variable is the thing that we're trying to identify, the number that we're trying to identify for each individual, and the individuals are the things that we are observing. Moving along to the next page, question number 29, it gives us another confidence interval to calculate, and this confidence interval can be calculated in the same way that we did before. Put it into the calculator, into that same screen, into stat tests, t interval, and you're able to get these numbers very easily. Then it asks whether the grading time exceeds 11 minutes. Every number here in the confidence interval is above 11 minutes, so yes, we're confident in that. For number 30, we do the same thing. Here's their confidence interval. And it asks us whether the confidence interval provides sufficient evidence that the mean number of home fires is greater than 5,000. Well, the confidence interval isn't exclusively above 5,000. There are some numbers that are below 5,000. So that means it's possible that the true mean number is less than 5,000. We are not given sufficient evidence to prove this. Last but not least, we're looking at testing of hypotheses. And this is another example where you're going to use the calculator and you're not going to have to get into too much of the mechanics of it. First, we write our hypotheses. Remember, the null hypothesis is the thing that we're trying to disprove. In this case, we're trying to disprove that the savings account balance in 2013 is the same as 2012. It says we're trying to prove that the mean savings account balance is different. So the first thing is, well, they're the same. And the second thing is, well, they're different, not equal to. Not equal to means we're performing a two-tailed test. And in my calculator, I'm going to pull up my calculator again to show you. In the calculator, I just go stat, tests, and we're doing a t-test. We're not going to use two sample tests for this class. Again, we're going to put in our stats, and here's the screen that you see. The screen is already pasted in here, so it's not necessary for me to put it into the calculator again. We're just putting all the information in here and then pressing calculate, and we get all this information out. The important information from this test screen is the p-value. The p-value is 0.000131104. That's very low. Remember, this -4 means times 10 to the -4, or in other words, move the decimal point 4 spaces to the left. So that's why there's 3 zeros and a 1. The conclusion is always going to be based on whether the p-value is less than or greater than alpha. They give us alpha here, which is 0.1, and we know that 0.0001 is less than 0.1. If it's less, we reject. If it's greater, we fail to reject. In this case, we reject the null hypothesis, and here's a trick. We have sufficient evidence to believe that the mean savings account balance in 2013, all I'm doing is taking this exact sentence and basically copying and pasting it here. As long as we say we have sufficient evidence to believe or conclude, and then the last part should be basically that same sentence. Let's see how it works again. Here's question 32. Similar setup, 46 cents per pound. That's the null hypothesis. The alternative hypothesis is we're trying to figure out whether the price of bananas has increased. It says increased here. That's why I'm using greater than, not unequal to. And notice there's a little difference in the t-test screen here. I didn't use this not equal to. I used this one greater than because we're trying to figure out if the alternative hypothesis is greater than. We do our t-test in the calculator and we get 0.0094, and that's our p-value. Again, our p-value is less than our alpha. In this case, alpha is 0.05. They're generally going to give you alpha. If they don't give you alpha, use 0.05. In this case, we're rejecting again. We have sufficient evidence to conclude that the current mean retail price of bananas has increased since 1994. I'm just using the same exact sentence. Shouldn't be that difficult. Looking at question number 33, remember, the context is important, but at the same time, all of these context boils down to the same type of concept. We're writing down hypotheses. We're performing some kind of test. Every time it's population standard deviation unknown, we use t-test. If we are doing proportions, if we're doing p-hat, we would use a z-test. In this case, it's a two-tailed t-test because we're using unequal to. In the previous example, since we were using greater than, it's a one-tailed test. The particulars are not that difficult. We make the t-value here. We go into the t-score or the t-test screen in our calculator. We plug in our information, and we get 0.0687. Now, this is a little bit different than the previous two problems because now the p-value is greater than alpha. Alpha is 0.05. So if the p-value, the probability that something weird like this happens, is greater than 0.05, we'd have to fail to reject the null hypothesis. We never accept, we fail to reject. There's not enough evidence to reject the claim that, we go back here, the average wind speed in a certain city is 8 miles per hour. Again, I'm just copying and pasting the sentence. Moving on to question 34, it says that on average a woman visits her physician 5.8 times. That's our X bar. The random sample 20 women is here, and you can go into one of our stats to easily find these values, 3.85. The standard deviation is 2.52. That's the SX. We're not using this, which is population standard deviation, because it's not a population, it's a sample. The alpha value is 0.01, and we're using the same exact screen as before, that t-test screen. As a quick note, all of the examples on this sample final were based on means. If you were trying to do proportions, there wasn't anything on that here, but what you could do is this. Go into stat, tests, a one proportion z-test, and then you would put in all the information from the proportions, the null hypothesis proportion, your sample proportion, etc. Anyway, this is very straightforward. My p-value is 0.0013, which is too small. We reject the null hypothesis. Hopefully you get the pattern here. All we're doing is looking at the null hypothesis, looking at the p-value and the alpha, and seeing if we reject or fail to reject. All right, that was the third and final part of the final exam review video series. Good luck studying.